Welcome to This Explainer. Okay, we're jumping right in today. We are going to unravel a totally fascinating scientific mystery. It's actually something you could test right in your own kitchen or school lab. We call it the frozen race, and we're going to explore the kind of magical concept of freezing point depression. So if you've ever wondered why ice and salt are such an intense, powerful combination, you are absolutely in the right place. Let's get to it.
I want to kick things off by throwing a really simple, but honestly kind of counterintuitive question your way. What actually happens to the temperature when you add salt to ice? Just think about that for a second. Your first instinct might be, well, nothing happens, it's just salty ice. Or maybe you're thinking, hey, we use salt to melt ice on the roads, so the mixture must heat up, right? Keep that prediction locked in your head, because we're going to set up a little experiment to find out exactly what's going on.
Section 1. The Frozen Race Setup.
So, to figure this out, we're going to run a virtual race. We're pitting two identical beakers of ice against each other, just to see how they behave under slightly different controlled conditions. Picture this in the lab. First, we take two standard beakers and pack them both with equal amounts of crushed ice. Simple enough. Next, we slide a regular lab thermometer right into the center of the ice in both beakers. That gives us our baseline. Now here comes the crucial variable. In the first beaker, we do absolutely nothing. It's our control. But in the second beaker, we add several big spoonfuls of common table salt. Scientifically, that's sodium chloride, or NaCl, and we give it a really gentle stir with a glass rod.
Now, before we check the results, I have to throw out a massive safety warning. Avoid prolonged direct contact. Why? Because ice-salt mixtures become extremely cold. Like, seriously cold. If you were doing this in a real lab, you'd actually need to handle these beakers with extreme care and clean up your workspace right after. This isn't just your standard winter chill, it is a biting, extreme cold. So that warning right there, that's a huge hint that something drastic is about to happen to the temperature readings in our second beaker.
Section 2. Observing the big drop.
All right, the stage is totally set. We've got our plain crushed ice for beaker 1 and our salty ice mixture for beaker 2. We're going to watch these thermometers over the next few minutes. Prepare yourselves because the results of this seemingly basic setup are bizarre. They're just incredibly cool to witness in real time. Beaker 1 with the plain ice is hovering right around exactly what you'd expect, the standard freezing point of water. Makes sense. But look at beaker 2. Our ice and salt mixture is acting completely differently. As we record the temperatures at regular intervals, we see the temperature of that ice-salt mixture drop significantly lower than the plain ice. We're talking drastically colder than ordinary ice. No way, right? But it's happening.
So, seeing that massive drop naturally leads us to a big, structured question. Why did the temperature of the ice-salt mixture become lower than the plain ice? Think about it. Both beakers started with the exact same crushed ice. Literally all we did was add common salt to one of them. So what secret role did the salt play, and where did this extreme drop in temperature even come from?
Section 3. Decoding Freezing Point Depression.
It is officially time to decode this mystery. We're going to break down the core chemical principles that cause this wild temperature drop and interpret what's happening inside that second beaker. The absolute key here is understanding the specific scientific term for what we just witnessed. It's called freezing point depression. And that's exactly what it sounds like. It occurs when the presence of a solute lowers the freezing point of a solvent. In our little experiment, the solvent is the water or the ice, and the solute is the salt we added. Just by introducing that solute, we radically change the physical properties of the solvent, basically forcing it to require a much colder environment to freeze solid.
Now, what's really fascinating is the broader scientific category that this whole phenomenon belongs to. They're called colligative properties. Let's look at this definition together. These are properties that depend on the number of dissolved particles rather than their chemical nature. Let me emphasize that because it's a game changer. It's not about the specific fact that we use salt. It is entirely about the sheer quantity, the actual number of particles the solute breaks down into when it mixes with the water. Basically, the more particles you throw into the mix, the greater the freezing point depression.
Section 4. Colligative Properties Explained.
To really grasp how incredible this is, we've got to shrink ourselves down. Let's zoom in and visualize exactly how this invisible chemical battle plays out at the microscopic level between the water and the solute. Here's the step-by-step breakdown. First, the solute particles are salt. Enter the water. Once they're in there, these particles literally interfere with the freezing process. Picture water molecules trying to lock together to form a neat, solid ice crystal. The salt particles act like tiny physical obstacles, just constantly getting in the way and blocking the water molecules from connecting up. Because of this constant physical interference, the water requires even lower temperatures to finally overcome those blocking particles and freeze solid. It's like trying to put together a jigsaw puzzle while someone keeps throwing extra pieces on the table.
Section 5. Real-world freezing magic.
Okay, so now that we've conquered the microscopic chemistry, let's zoom back out to the real world. This isn't just some fun lab trick to do in class. Applying our understanding of freezing point depression actually unlocks some of the most important everyday miracles and engineering solutions that we rely on all the time. For instance, in cold countries, spreading salt on icy roads is a brilliant way to de-ice them. It lowers the freezing point, meaning the water stays liquid even when the air around it is freezing cold. This exact same property is famously used in food prep too, like when making homemade ice cream. The salt forces the ice mixture's temperature incredibly low, which freezes that sweet cream perfectly. And in the automotive world, we use antifreeze solutions to make absolutely sure your car engine's fluids don't turn into a solid block of ice during the winter.
But it goes way beyond just keeping our roads safe and our ice cream perfectly chilled. This concept carries massive scientific and industrial weight. Out in the field, understanding colligative properties actually helps scientists accurately determine the molecular masses of unknown substances. It's absolutely crucial for understanding overall solution behavior across chemistry and industry. And on a massive scale, it's widely used in huge industrial refrigeration processes. The whole shebang relies on these tiny particles getting in the way.
Well, we have covered a ton of amazing ground today, going all the way from 2 simple beakers of crushed ice to the microscopic disruption of water molecules. But before we wrap up this explainer, I want to leave you with one final puzzle to test what you've learned. What would happen if we used a totally different solute, like, say, sugar instead of salt? Now, remember our definition of colligative properties. The effect depends on the number of dissolved particles, not their chemical nature. So think about how sugar breaks down in water compared to common salt. Does it create the same number of particles? I'm going to let you ponder that one. Thank you so much for joining me today. Keep asking those big questions, and I'll catch you next time.